Hey guys, I'm back again to go over another AP Physics 1 free response question. This time I'll be going over 2017's question number 3. So in this question, we're given that a disk traveling at V0 is going to collide with a rod that's swinging on a pivot. So in part A, we're asked where the disk should hit in order to give the rod the most angular speed after the collision. Well, we know that the angular acceleration, which is proportional with the angular speed, is also proportional with the torque. So we want to find a way to maximize the torque. Now the equation for torque is T is equal to R times F sine theta, where R is the distance between the disk's collision spot and the pivot. So we want to maximize this as much as possible. And if we go back up, we see that if it hits to the right of the disk, then the R value of this equation will be much greater than if it hits to the left, because R will be this. So this question will be to the right of C. So in part B, we're given an equation and we want to find if this equation makes sense. Well, we see that the angular speed is equal to the mass of the disk times the distance of collision times the initial velocity all over the moment of inertia. Well, we see that as the mass of the disk and the distance increase, the angular speed also increases, which makes sense since in our previous equation we found that the distance should be maximized in order to give the greatest angular velocity. So this one is yes. Now moving on to part C, we see that another student gave us another equation and we need to find if this one makes physical sense or not. Well, we see that this time the mass of the disk is in the denominator of the equation, which does not make sense since if we increase the mass of the disk, we would expect it to give more angular momentum to the rod, and therefore the rod should increase in angular velocity. So this one is no. So for parts D and E, we're not going to assume that the rod is much more massive than the disk, which means that there will be some significant increase in the angular velocity of the rod. Now for part D, we're going to need to find an equation that represents the angular velocity of the rod and disk system after its collision. Well, in order to do this, we're going to have to use the conservation of angular momentum, which looks something like this. L1 is equal to L2. And we want to find the values that make up each side. Well, initially, the rod is still while the disk is moving. So we know the rod is not going to have any angular momentum, while the disk, since it's moving in a straight line, its angular momentum is just going to be its linear momentum multiplied by its distance. So that's going to be m times v0 times x. And then the right side of our equation will be the disk and rod system, where the moment of inertia is their added moment of inertias, which would be m times x squared plus the moment of inertia for the rod, which is just I, and then this is multiplied by the angular velocity of their equation. And so if we want to solve for the angular velocity, we just divide this and get this expression right here. So for part E, we want to find that if the disk, instead of sticking to the rod after the collision, if it bounces off, so it would look something like this and it would bounce off, would this give more angular velocity, or would it stay the same, or would it be less than? Well, we know that if the disk bounces back off, then its angular momentum will have to be subtracted since it will be negative in comparison to the rod. And since the left hand side of the equation is constant, we know that this means the angular momentum of the rod will have to be greater than what it is. So this will be greater than. And that's it for this video. Thanks for watching, guys. See you in the next one.